Hi guys, welcome back. We are gonna now first discuss a new collection of special bounded linear transformations on Banach spaces, and that new family will be useful in proving some further properties about compact linear transformations. Now that family, which is written here in the very first definition on top of the page, so if you have two Banach spaces, then Fa, x, y are called the finite approximable linear transformations. And what's that thing? Well, that set is the norm closure in Lxy of the finite rank linear transformations. That is to say that the elements of Fa, x, y are either finite rank linear transformations or they are norm limits, norm being here the operator norm, of finite rank linear transformations. All right. Turns out this set is closely related to the compact linear transformations. In general, it's not equal to the compact linear transformations, but before we get there, first a few properties. And these properties, they should really ring some bells, because we had quite similar properties for the compact linear transformations. So first off, you have three Banach spaces, x, y, and z. And then if you have something, well, either a finite rank or the norm limit of a sequence of finite rank linear transformations, then this is also going to be compact. That's not surprising. Property number two, Fa is a norm-closed subspace. Well, norm-closed is built in the definition. It's written there, is the norm closure, so that doesn't need any further justification. What needs to be justified is whether it is a subspace. So taking two elements in there, forming a linear combination, is that still going to be in Fa, xy, or are we going to fall out of it? I will show it in a minute. Then again here, Fa forms a two-sided ideal. So if you have an Fa, a finite approximable linear transformation, and you compose it either from left or right with something bounded, then the result is still going to be finite approximable. All right, very much like what we had with the compact things. And then the fifth property, if T is finite approximable, then the same is true for its dual transformation. Note here I don't write if and only if. That was the case for the compact ones, because I will leave that question probably to the exercises. So you will have to decide whether, if the dual transformation is finite approximable, whether the original T is also finite approximable. All right? Good, so now let's get started. First off, many of these properties are clear from the get-go. So since any, that's what I already said earlier in words, any element in Fa by definition is either of finite rank or the norm limit, that is to say an operator norm, or the norm limit of a sequence of finite rank linear transformations, Claim 1, that is that Fa is contained in the compact ones. Claim 1 follows at once from the properties of COM_XY, because COM_XY itself is a norm-closed subspace, right? So that's what I already said when we had this theorem. So a finite rank operator is always compact, and since COM_XY is a norm-closed subspace, any sequence of finite rank operators, which are themselves compact, if it is convergent, it's gonna again converge to something compact. So indeed, this is a norm-closed. This Fa is a subspace of COM_XY. All right, good. So then we have this. Next, Fa, I already said it in words earlier, is norm closed by definition. Norm closed by definition. And if, now what about subspace? So if S and T are finite approximable, and first of all, if both are of finite rank, then for any do check this. This is actually a fact that you can already discuss in linear algebra. So how can you relate the range of alpha s plus beta t? Well, I claim this is a subset of the vector space sum of range s and range of t. Alright, this is a property that you can already discuss in linear algebra. So consequently, because these here have finite dimensions, hence any subspace, any subset in particular thereof has to have finite dimensions. So that means in particular alpha s plus beta t is going to be finite approximable, actually going to be a finite rank. It is alpha s plus beta t is a finite rank. Maybe I shouldn't write this element. I would say is a finite rank, and that means then it is in Fa, is a finite rank. So alpha s plus beta t in Fa xy. Now, okay, that's the easy case when both of these guys are finite ranks. So what happens if at least one of them is the norm limit of a sequence of finite rank linear transformations? So on the other hand, if at least one of s comma t is the norm limit of a sequence of finite rank linear transformations, yeah, but then you just add two sequences, right? Finite rank linear transformations, then clearly if you just add sequences together, to each term in the sequence you add one of the other one, then clearly alpha s plus beta t is also the norm limit of a sequence of finite rank linear transformations. All right. We have verified the second claim, that it is a norm-closed subspace. We have verified claim 2. Now, the ideal thing, that is very easy, and again it uses knowledge actually from linear algebra. Next, if t is bounded and s is finite approximable from y to z, then I claim the composition is finite approximable from x to z, since, well, there's the following subspace inclusion holds true. So the range of the composition is a subset of the range of the guy which is to the left. So think about this. I mean, it's easy, right? So if you have an element in here, y, then y is of the form stx. Yeah, then you just use a bracket here. So that immediately tells you that y is in the range of s under this point, right? So that's why you have this trivial subspatial inclusion. Yeah, but now that's all that you want, right? Because this guy here on the right, it has a finite dimension, so then any subspace thereof, which is sitting in it, also has to have finite dimension, and that's precisely what's written up there. Okay, good, so that's easy. And likewise for S in Fa(xy), T Ly(z). So now we do the other way around. I claim that the composition Ts, so the finite approximable one is now on the right instead of on the left. So this is Fa(xz) because, well, the same argument that I showed earlier. actually shows this one, which is improved, and you can still see it here in yellow, right? So I had y is equal, okay, now here s and t are relabeled, but so what, the argument is the same. So you have stx, and then it is s of t of x, yeah, but this element here is in the range of t, and that's precisely what goes in there if you swap the roles of s and t, right? So this is true, well, then you're done. Why? Because this guy here inside, it has finite dimension, right? And then of course t is gonna map it to something finite dimensional. You can't map finite dimensions to infinite dimensions. That's not gonna work out, right? So that the right hand side again has to have finite dimension, and then so has the left hand side, and that's precisely what's written up there. Okay, good. So this is all clear. So this completes the proof. What I said is you can't map finite dimensions linearly to infinite dimensions. Okay, so that's more precise. We're doing here linear maps. Linear maps are going to map finite dimensional spaces to finite dimensional spaces, not to something infinite dimensional. And that's simply because of the linearity. If you have finite dimensional space, you have a finite dimensional and a basis with finite elements. Any vector in there is a linear combination of those finitely many basis elements. So if you act with the map on it, it's going to give you a finite sum, right? So the range is finite dimensional. Okay, this completes the proof of 3 and 4. Okay, so finally, this is the fifth property. You need the compactness of the dual transformation given the compactness of, not the compactness, the finite approximable property of the dual transformation. So if Tn is a sequence, of finite rank linear transformations with Tn goes to t as n tends to infinity, then what can we say about the sequence of the dual transformations? Well, first off, it is a sequence that we know, of course, in here, and I claim it also, maybe I shouldn't write the sequence, just Tn. How about that? That's probably better. Then Tn in L y star x there also has finite rank. Why is this? Since, and this I will put on the exercise sheet, it is not hard to see that the dimension of the range of T is equal to the dimension of the range of its dual transformation. This just uses the definition of the dual transformation, how it acts. Okay, so if one of these two guys, one of the sides is finite dimensional, the other one has to be finite dimensional as well. Right, so this will be in the exercises, all right? Hence, what we have is that Tn, the dual sequence, remember the map that sends linear transformation to its dual, it's an isometry, so that means this is true, and henceforth this goes to 0, right? So that means in turn that T of t, because remember we already showed Fa is a norm-closed subspace, so if I hit any element with a sequence of finite rank linear transformations or norm limits thereof, then the limit is again gonna be finite approximable, right? Okay, so we have this. This completes the proof of the theorem. Okay, excellent. Now, what I anticipated so far is what comes next, right? So I said we will have a little test to show whether certain things are compact, because at the moment we don't really have any tools for these. Even for these integral operators, we had to use our Ascoli theorem, which is highly non-trivial stuff, right? So, but so far, what do we have? So we have now 3 sets. We got these guys. We got these guys, and from early on we got these guys, right? These 3 things here. Okay, so now what we have shown so far is this and this inclusion, and we also know that in general, if for instance these are infinite dimensional Banach spaces, then not every bounded linear transformation is a compact linear transformation. So that means this is a proper inclusion here on the right. Okay, so now of course you can ask the same thing: is this here proper or not? Okay, now it turns out this is actually a very hard question. It's a very hard question. This was, I think, resolved in the 1960s, early 1970s, and the answer is no. In general, this is also a proper inclusion, but this is really hard to prove, and we will not prove this in this class. Instead, what I will do is I will single out a class of Banach spaces where this is actually an equality, right? So, and that in turn then means that if you are in this class of special Banach spaces, which are Hilbert spaces, so that they're very nice, you can, at least theoretically, approximate anything compact by a sequence of finite rank linear transformations. Once this is established over Hilbert spaces, right? That's what it means. So there's at least one way how you could prove that certain things are compact, approximated through a sequence of finite rank linear transformations. And if you are doing this over Hilbert spaces, then at least abstractly you're guaranteed that such a sequence exists. And this is because of the upcoming theorem. Okay, so that's an important theorem. It is, I will call it the approximation property. Okay, and again, not every Banach space has the approximation property. This was a open question for many, many years. It was settled, I think, in the 1960s, but this goes beyond the material of this class. Instead, what we will show is Hilbert spaces have the approximation property. So let H be a Hilbert space, and Y just a Banach space. You don't need an inner product on the target space. Then Fa of Hy is exactly the same as compact Hy, right? So the only thing that we have to show is we have to show this inclusion here, right? The other inclusion we already have. That's an easy property of finite approximable linear transformation, right? So that's the approximation property. Again, it does not hold true if you remove the word Hilbert space there, right? For generic Banach spaces, this is not true. Generic Banach spaces don't have the approximation property. Okay, Hilbert spaces do have the approximation property. Okay, so proof. This will take some time. So we will show, that's what I already said, that any T in compact Hy is the norm limit, and we will construct that sequence explicitly. Right? So this is actually a constructive proof. Is the norm limit of a sequence of finite rank linear transformations. All right, so first of all, we may assume that our Hilbert space is infinite dimensional. Why is this? Well, remember what I said earlier, if you have linear transformations and they act on finite dimensional spaces, then their range is going to be finite dimensional, right? So, and then if you have maps between a finite dimensional space and a finite dimensional range, that guy is always going to be compact, right? And in particular, finite approximable, right? So there's nothing to prove if H is not infinite dimensional, right? So assuming H is infinite dimensional, we select a sequence xn of vectors. Well, actually, no, I don't need a sequence, just collection. I'm not gonna study the convergence of these xn's, but something related to that. So we select collection of points and orthogonal projections. So remember we discussed projections not a while ago. So those are bounded linear transformations, executed twice is as good as executing them once, and if they are orthogonal, that means they are self-adjoint. Right? Orthogonal projections, Pn, and those are actually operators in our Hilbert space as follows. That's quite a remarkable construction. The first time I read it, it's quite neat. So in the first step, okay, so we gotta start somewhere. So just pick a random point, x1, normalize it, so it shouldn't start with 0, and pick it in such a way that tx1 in y norm is at least a half the operator norm of t. And this is certainly possible. We used a similar argument when we were proving the big theorems in Banach space theory, because if for all vectors x you have the reversed inequality, you optimize over the unit ball, and then you get a contradiction in that the operator norm would be strictly less than half of the operator norm. So this x1 certainly can be chosen in the indicated way. Now define the first projection, P1, LH, just the orthogonal projection onto, well, the span of x1. So that is a known business from linear algebra. Orthogonal projections on finite dimensional subspaces, they come with explicit formulas, right? So I won't explain any further why this guy that I'm about to write down is an orthogonal projection onto span of x1. Okay, this is known from linear algebra. You just take the Fourier coefficient x1 and multiply it by x1. All right, good. In the second step, now this is quite neat. Pick x2 in H with, well, x2 has norm 1. It is in the kernel of the first orthogonal projection, and that just means, if you look at the map up here, that just means that vector x2 is orthogonal to x1. Okay, and tx2 in y does not exceed 1/2 the operator norm of not t but identity minus p1. Okay, why is this possible? Also, this is possible because you're in a Hilbert space, so you have the projection lemma. So let's write this out. T1 minus P1, what is this? Well, by definition, this is a supremum over the boundary of the ball. T1 minus P1x, y. But now remember, you're in a Hilbert space, so you can write everything as a if you start with an arbitrary closed subspace, and then you have a complementary subspace to it. And here I will take the closed subspace as the kernel. Kernels are always closed. Plus, but the kernel of identity minus P1, and then because this is a projection. If P1 is a projection, then 1 minus that thing is also projection. So you have, by general theory that we discussed a little bit earlier, that these two are complementary subspaces. Yeah, but remember, there's this cute property that the range of 1 minus a projection is just the kernel of a projection, right? So, but now look, this means every vector x in your Hilbert space you can write as a sum of something which is in here and something which is in the kernel of P1. Yeah, but the part where you go over the kernel of P1, it would not contribute to your optimization procedure here to get the operator norm, because it would be sent to 0, right? So that's certainly not gonna contribute. So having said this, this supremum here is the same as just a supremum where you range over the vectors that are in the kernel of P1 and have length 1. This is exactly the same thing because of what I wrote up there in yellow. Right, so you have this. Yeah, but now if x is in the kernel of P1, then of course this piece here is equal to 0. So this is just a supremum over that boundary. P1 of x equal to 0, and then just t of x in y. Okay? And so now you should read this here is precisely equal to this there, and that's why you can choose this x2 so that this guy here is satisfied, right? If not, then you argue just like in the first case and you get a contradiction to the red underlined thing that I wrote here below, okay? Now once you have the vector x2, you use the Gram-Schmidt procedure and you orthogonalize it to the first vector x1, because that's precisely what this thing here says, that x1 and x2 are orthogonal, and that you can certainly do for finitely many vectors. And once you, the x, by the way, is not going to be 0, the x2 is not going to be 0, and then at the end you normalize it to 1. And that's how you can satisfy those three properties. You start with this one, then that one, and then that one. Okay, that's it. Okay, excellent. Good. So now continuing in this fashion, so proceeding inductively, I probably won't be able to finish the proof, but let me at least write down what we get from this inductive procedure. Proceeding inductively with Pn. So from this procedure we get a collection of points x sub n, and then we define the next orthogonal projection. Orthogonal projection onto span x1, xn. So also this guy of course has a formula. Pnx, that's known from linear algebra, it's just the sum of those Fourier coefficients. And then with xj, notice by the way, this is of course a finite rank thing. So in particular finite approximable, right, for any x in h. We can choose, and that is what I mean inductively. So once you have the first n terms and that p sub n, then you choose the next one, x sub n plus 1, so that it has length 1. It is orthogonal to everything previously. This is what the Gram-Schmidt does. And you have this curious inequality, xn plus 1, y at least a half t1 minus pn. Okay, that's what you get there. All right, so I will stop here. There's a little bit left in the proof of this theorem. We have to now show how we actually approximate our initial compact thing T with a sequence of finite rank linear transformations. I will define this sequence, then we will prove the convergence in operator norm, and then we're done with this. After that, then the really big theorems about compact linear transformations, in particular operators, start appearing. We will discuss the Fredholm alternative. That's the first very big thing. That will take quite a while to prove it because it needs several preparations. And then once we have the Fredholm alternative, then we start the spectral theorems. Okay, existence of eigenvalues, eigenvectors for compact self-adjoint operators on Hilbert spaces, and then we will have the spectral theorem at the very end. Okay, so we're heading, in other words, we're heading to the very peak. Okay, I'm looking forward to the next video.